So now there's a thematic panel on programming tools and workflows in science. This will be chaired by Daniele Lecci, who is a senior researcher in workflows and distributed computing at the Barcelona Supercomputing Center. So Daniele, when you are your panel ready.
Thank you, Alberto. So welcome to this thematic panel on programming tools. So we want to present 4 use cases on different applications science. We will have the first presentation of Josep Lapuente from BSc, then Riccardo Rossi from UPC SINME, and Davide Cirillo from BSc. Davide, you are there. Couldn't find you. And then Stefano Lorito from INGV Italy will have the final presentation. So please, the speakers, we will start with Josep Lapuente from BSc, presentation of Argent physics-based simulation of earthquakes. So Josep is a computational physicist interested in geophysics. He holds a PhD from LMU. München, and he leads the multidisciplinary team at the BSc on that includes IT experts, physicists, mathematicians, etc. So please, Josep. So the slides are here. We will have the question at the end of all the presentation, okay? Thanks.
Okay, thank you very much, Daniele, for the introduction, and thank you all the sponsors and organizing of this event today. Very happy to be able to share and open the floor for this interesting event. So I'm going to talk to you about simulating earthquakes and about doing so urgently, okay? So both topics are, I think, relevant for today, and hopefully we will get some understanding of that and some nice discussion afterwards. So simulating earthquakes is something which we can do physics-based, let's say, based upon Newton's equations, Hooke's equations. For a long time, since the early 80s, there have been efforts into simulating a given earthquake at a given moment, okay? We can do this very easily and very well if we know everything about the parameters controlling that earthquake. So if we know the magnitude, location, characteristics of the fault, if everything is well known, simulations are fairly accurate, okay? Physics don't lie in this aspect. What has been happening in the recent years is that from just purely scientific studies about understanding why earthquakes behave in a certain manner, why somewhere very close to an earthquake sometimes people are not really affected by it, and suddenly a little bit farther away there's a surge, let's say, in seismic energy, and we want to understand that. Why did this happen? It mostly has to do with physics, and that is what we have been simulating for a long time. This effort has later on been applied to hazard studies, to trying to understand more about the potential for a certain event to happen, okay? We cannot predict earthquakes. We will not do that anytime soon. That is something which is, let's say, out of our capabilities, scientifically, observational capabilities, actually. But we can do something about understanding what could happen, okay? And that's hazard studies. This has been happening a little bit more recently. And what we want to do is be a part of an effort to incorporate the simulations into resilience. So acting after a certain earthquake has just happened, okay? As it happened in Morocco, for example, unfortunately, during last week. So what we do for that is what everybody does. I think everybody in the room can decompose their problem into analysis, pre-processing, processing, post-processing. That's, okay, what everybody is doing, let's say, in science or in any actually field, probably, which is related to computing. We are not, let's say, different in this, but we call this a workflow, okay? The key thing here is realize that we have been spending a lot of time in optimizing the part of this process which is related to HPC alone, the solver. In this case, we're using Salbus here. It's a nice technology, highly scalable, very efficient. It uses very well the supercomputer. But us, researchers and technicians, spend most of our time in the other parts, and we are not optimizing that at all, okay? So that is the part where workflows come in, and when designing and actually taking apart the small tasks which involve the end-to-end process need to be unfolded, and we can then aim at optimizing this, hopefully automatize this procedure, okay? This is what comes up when we try to extrude, let's say, all the tasks needed since recording an actual earthquake, which just happened, to deciding whether this earthquake may or may not be something which we should worry about, given many circumstances, distance to some populated areas, magnitudes, and so on, until the very end. And at the very end, it's not us using this process, but someone which can do something about this information. I cannot do anything about an earthquake hitting very severely a region, but there's people which definitely do, okay? And these are disaster relief agencies. So our task here is being able to decompose this process formally and being able to give shape to something. This workflow has to, let's say, have an implementation which allows us to avoid issues related to unexpected problems, so resilience of our process, and heading towards automation. We want to reduce the time which takes end-to-end for this process to happen. We want to have as few as possible human interaction for this. And of course, we need to be able to run these things urgently in a supercomputer. And that last bit is not yet there. Hopefully it's happening soon. We will discuss about that later. So just very briefly, the alert system essentially just grabs information. Seismic networks are open. We can have early access to this. In a few minutes, we get to know that an earthquake has happened. And the estimates about magnitude and location are fairly good. Depth is not so good. Focal mechanism is definitely unknown. But this helps us, let's say, kickstart our process. Okay? This is part of the workflow, observing this automatically and deciding upon when something is really important or relevant. Then, of course, we need to pre-process this thing, and this involves many things. From the purely simulation side, you have to think that these are three-dimensional simulations happening in a large mesh. We need to build those meshes. We need to incorporate parameters which are related to the geological properties of the area, and so on. But also, we need to fill the gap between this early, let's say, knowledge about what the earthquake is, magnitude estimates, location estimates, and that's it, to something which is more akin to what in physics we need to know about an earthquake to be able to simulate it accurately. And this mostly is related to the fault parameters. So an earthquake essentially is two slides or two blocks of a huge rock which are sliding upon each other violently, okay, at scales which are much faster than what typically happens in tectonic settings. We need to know the details about that. So at this stage, what we can do is guess them. And we make several guesses. And we try to run all of them at the same time. We do this at the supercomputing center, such as BSC. We need to run those simulations simultaneously. We need to use as much of the machine as possible if we need to have a very short time to solution. And when lives of people matter, it is very important that we are efficient at doing this whole process, okay? Later on, we gather the byproducts and we produce maps, okay? Maps which tell you what has happened, okay? So I'm going to show you just one case in detail. The others I will just browse through because there's a lot of time for other people to give their presentations, and they're worth listening to them. So this is a case of an earthquake which occurred in Turkey. Turkey is very prone to earthquakes. You should know that already. This happened in completely the opposite side of the last one. So this is closer, let's say, to the border with Greece at the Aegean Sea. And this is, let's say, a little bit north of the Samos Island. But it affected mostly a location which is a little bit inland, let's say in the Anatolian Peninsula, called Izmir. Magnitude 7 earthquake. It did kill a few people, about 100, a little bit more, damaged a lot of properties. What we try to do here is emulate what would happen if we would have this urgent resource available. Let's imagine that you know, when we click a button, Mare Nostrum stops and gives us the resources, and we can run things, okay? We did that at the downtime of the system. So the system needs some maintenance once in a while. At BSC, we have the privilege of having both the infrastructure and the researchers. So some of them take care of the machine, some others build software and evaluate it. So that, let's say, connection allowed us to do this, the simulations, which took most of the machine for about 3 hours to run these 132 possible cases, which could represent this earthquake. What we obtain is this map that you have on the left, which essentially is affectation of this event at the rock. It's not the end, let's say, of the result. This is not really telling you in red places people die and in green ones they don't, okay? But it's a step towards this. To the right, what you have is what USGS, let's say the well-known geological service, gives you as an early forecast. As you can see, the amount of detail is very different, okay? And we're not using any data here. No more data than an earthquake happened with a certain magnitude at a certain location. We fill the gaps, okay? And this is our estimate. That's a simulation. This is an outcome, which of course has error bars associated to them, and it's lacking everything related to, for example, amplification effects, which cannot be simulated at the scale at which we are doing this thing, and also the damage or the vulnerability, let's say. We don't include here whether a building is weak or not, okay? But still, we can perform the simulations. As you can see, when we incorporate data for that particular region, apparently, the simulations are able to more or less, or rather accurately, I would say, reproduce what has actually happened in that region. Again, from first principles. This is physics. This is nothing more special. In here, we have some comparison of peak velocity register at the ground, both synthetic and the center and simulated, synthetic and observed at the right. And you can see that in this region, which was where most people died, actually the numbers are very similar. Those numbers are not, again, not the real thing. I mean, so the actual accelerations there were much bigger, and that's related to, again, amplification system, related to the soil itself where, let's say, the city, unfortunately, was founded. But this is just to showcase what we can do if we are provided these resources. We have other examples. I will not spend time with that, just for you to know. We can test this more or less universally in other regions as soon as we have the knowledge, okay? About an hour time end-to-end for the simulations, up to 5 hertz, which is reasonable for many infrastructures. We can keep improving that, okay? This is just a fit of this. Let's say when you see the red dots, is our best guess, let's say, with other means, empirical means. And in here you have, let's say, the disaggregation of our results. So actually, numerically, our results are very efficient. And we have carried this ideas or this process to other cases in Iceland as well, a doublet, which is 2 earthquakes happening with few days differences. Again, we were able to, let's say, do a good estimate of the expected ground motion based upon physical principles. So just to close on what we've been doing, we've been focusing on establishing these workflows, automating a process which can help saving lives. We've done this with the help of these projects, CHEES, eFlows for HPC, COIOS, DTG, who is behind Daniel as well. And essentially, we are now at the process of engaging with the actual end users of this thing. In Spain, this is a military emergency unit. This is UME for us, and other institutions associated with that. And we are expanding the amount of regions where this can be applied, okay? But first and foremost, and this is what I think we should discuss later on probably, we do depend strongly upon this different way of using the supercomputers. This way of using supercomputers, which is not in the list that we have seen, let's say, in the presentation before by the RES or by Euro HPC. So it's been under the discussion for a long time, and I think it would enable a lot of, let's say, uses for disaster resilience. Think about biohazards, think about nuclear hazards, think about natural hazards. And with that, I want to end. Thank you very much.
Thank you, Josep. So, as I said, question at the end of the presentation. So, next presentation from Riccardo Rossi from SIMNE. Riccardo is full professor at UPC and SIMNE, and expert in development of HPC simulation code. Is one of the main contributors of the Kratos multiphysics software. Today we'll present the use of HPC for flows for the simulation of simulation-based reduced order models. So it needs, yes, some animation, so. Huh?
My presentation is not
No, perché?
Well, okay. I will present it without animations, doesn't matter. So,
¿Cómo se pone toda la pantalla? No se ve, ¿no? ¿Cómo se pone?
So sorry, no, it's not.
Okay, no.
Yes.
So that is not on the screen. So sorry for the small delay. I will speak today about also a workflow which we are developing actually in the same project, but which is about the use of high-performance computing in order to perform reduced order modeling. So I need to first explain a bit what is the theory, and then I will try to explain why we need HPC and how we are handling the complexity of parallelism. So the idea is that we want to solve a complex problem. This is supposed to be an animation, but I'm afraid it will be lost. So this represents an engine, an electrical engine, large one, the size of a train to understand. And this is refrigerated by the use of air. So it is the same motion of the engine that provides a flow inside this stuff, and this is what keeps the temperature low. Now, simulating this as complexities, I mean, this should be seen rotating, but I'm afraid I have a little technical problem with that. And this rotation allows one to predict what is the final temperature that is reached at any point of the engine. This is important because eventually you will avoid overheating, or you will need to know if it is safe keeping operating the thing. Now, of course, when you change the parameters, so for example, when you change the input power or when you change the rotational speed of the motor, the thing changes, and you need a tool that allows doing a prediction. You can achieve this by simulation, and I mean, you can do one full-scale, full-order, we call simulation, for every scenario that you are interested in doing. However, what is the thing? The thing is that if you finally want to take fast decisions on the basis of these, you will need to pre-compute a lot of those models, and you will need to package those models so that the predictions can be done much faster. So the idea is as follows. While you could, well, that's the red line, simulate more and more scenarios, and this would have a cost that grows progressively with the number of simulations you want to run. You may also decide to pay an initial price, but then to have all the simulation predictions to be done much faster and possibly to run on the machine itself, the one you want to simulate. Well, this is to see that this thing works. You don't see anything. This, again, would be a video, but it would show that what you can achieve is that the reduced order model, so the fast prediction that you can achieve out of this, allows one to deliver the same result as you would obtain from a full order simulation. Now, let's have an idea about how this works. Well, essentially what we have is that there exists an operator that is an operator that we discretize. We call it a residual, which depends on the input parameters, which we call mu, and on a given solution, which we call u, and that will eventually depend on time. This is discretized in space and in time. We use the finite element method for doing this, and then it is discretized by a nonlinear solution procedure, which in our case is the Newton-Raphson or Picard. Well, the idea is as follows. You will simulate different scenarios. Every scenario is a dot on this. So for every scenario, you actually compute multiple time steps. But then what you do is that you collect all the results that you have for different input parameters into a matrix which collects all the data. It is like a collection of the movies that come out of all of the simulations. Well, what you do is that you eventually analyze this matrix and you find an operator, which the easiest one is the singular value decomposition, which allows this to compact, so to write it as it is shown below, as a low rank representation plus an error which you can control. Well, the trick is now that if the full order model is written as it is shown on the top as a residual in terms of an increment and of the parameters of your model, which needs to be set to 0, what we can do is that we can now rewrite the delta u, so the correction that we have with respect to the past, in terms of phi times delta q. This is a lower order representation, which is essentially saying that instead of having millions of degrees of freedom, you can eventually have 10 degrees of freedom, a much smaller number of degrees of freedom. This can be done with a linear operator, wow, or eventually with a nonlinear one, which is, for example, a neural network. To understand what this means that if the original problem implies at every step solving a linear system of equation like the one is showing, which is of size capital N, so that is large, what you're doing is that you're reducing this problem first to a rectangular problem in which the number of unknown is greatly reduced to a small n, and then you can reduce it to a small problem by projecting onto a given solution space. Here there is some theory. But instead of solving a large system of equation, you end up solving a small system of equation with a result that is very, very similar in the sense which is similar up to a controllable level of accuracy to the original problem. This can be done in different ways, which really exceed the interest now, but overall this implies that one has to mount a workflow. In particular, one needs first to simulate a lot of different scenarios. Here you have some parallelism. You have to collect those data to construct that matrix I was describing. You will need then to analyze that matrix to find further opportunities for optimization. This is known as hyper-reduction. And then you will have to validate your data and eventually to deploy it into practice. This defines a workflow as the one that is shown here. The idea is that the small system of equation I was describing is fast to solve, but is still expensive to construct. So instead of performing our loops over the entire number of elements that we have in our mesh, or if you like, if it was a Cartesian discretization, over the entire number of collocation points that you have in your discretization, you can carefully pick a few that are enough to reconstruct the solution, again, up to a controllable level of accuracy. This introduces a level of parallelism, because if that is your mesh, you can collect the examples, but then you can divide your mesh into subportions. You can do an optimization for every subportion, and you can eventually gather the thing. This defines a small workflow like the one that is shown here, and this eventually has to be analyzed by using a singular value decomposition, which can be done as a linear algebra operation, but when the size is so large as the one that we will want to deal with, then you will need techniques like the tall and skinny QR, which can be implemented in MPI or on the top of a workflow management system, as we are doing in our project. For example, in our case, this is being integrated into the DISLib computing library by the BSc, and this allows, or together with the randomized SVD, which is a different option, allows us to analyze an enormous amount of data which would be otherwise untreatable to us. Well, overall, this implies that all of this is included in a workflow management system in which there are tasks with a dependency between one of them. Some of those are integrating into the SVD, others are integrated in the hyper-reduction, others are simply the solution of the fluid. Each task has an inner level of parallelism, so for example, could use MPI or could use OpenMP, but eventually this builds a tree like this, in which you could recognize stages, and this is integrated, in our case, in a workflow management system that is called PyComs, and again is developed at BSc. Of course, this poses some challenges, which are the ones that are being faced in the project, which is that the entire thing needs not just to run, but to be performant and to scale up to a large number of processes. But also it implies some problems in deploying the entire stack, because now you will have to deploy your solver, but you will also have to deploy the workflow management system, the DISLib, a lot of different components that are into this, and this opens opportunities for investigation that are being addressed in the project. And this also opens the melon of performance portability, so essentially if this thing will work fine on one machine, if the performance on that machine is also replicable onto another machine. And then, of course, there are practical tasks like stupid things, but things about the MPI libraries being present or being incompatible between one system or the other, the many systems of whatever that are on a given system, and these are all things that need to be solved when wants to deploy an entire package and eventually to deploy it as a service as it was described in the previous call. And this brings to my end. So thank you for your time. And this is just the acknowledgement to the project eFlows for HPC, which is funding our research. Apologies for the missing videos.
Thank you, Riccardo. So, next speaker, Davide Cirillo from BSc. Davide is head of the Machine Learning for Biomedical Research Unit at the Life Science Department here at BSc. His research focuses on computational methods for precision medicine with a special emphasis on machine learning, network science, and the ethics of artificial intelligence. So his presentation is about the Sprint personalized healthcare use case for stroke risk assessment. No, c'est pas ça. Okay. No.
Quindi un PDF non ci sono
Sì, mi trovo tutto scritto. Ora sono là. ¿Cómo se pone todo tiempo? Que salte F8.
Okay, here we go. Thank you so much. So thank you also to the organizer for having me here today. I'm going to talk about the use case of a European project that is called AI Sprint. This is a healthcare-focused use case. So AI Sprint is a European project that has been founded by the Horizon 2020 Industrial Leadership Program. It's coordinated by Politecnico di Milano, and the Barcelona Supercomputing Center plays a major role in the project, both in terms of the technical work packages and also specifically in this use case on healthcare. The goal, the objective of the project is basically to enable the design and use of AI-based application in the so-called computing continuum. So the computing continuum, you know better than me, that it's essentially the computational space that goes beyond the two extremes of the cloud and the edge. And we can define those extremes essentially based on the distance to the sources of the data where it is produced. So generally the cloud is servers that are very far from the sources where the data is produced, while the edge is very close to the sources of the data. And the ways in which essentially we capture the data at the edge is through sensors. And those sensors can be, for instance, cameras installed on vehicles, or sensors that can monitor some interesting health parameters in wearable devices like smartwatches. So in terms of market, there is a big interest in edge computing, and in particular in the use of artificial intelligence at the edge. Which makes sense. I mean, this makes everything more portable, more flexible, but of course this comes with a lot of challenges, in particular from an infrastructural perspective. And those challenges essentially range from the mere know-how to the data volumes that you have to deal with, concerns about privacy and security, in particular for healthcare applications, the heterogeneity of those data sources, the elasticity of the resources, costs, energies, so a lot of issues. And the AI Sprint problem is tackling those challenges. Specifically, one particular challenge that is the following. At the end of the day, the actual program that runs, for instance, the training of an AI model or its use for inference is actually like a small piece in a big ecosystem of tools and assets that allows the use of this program. So as you can see represented here, this ecosystem entails many tools, many things that we need, from configuration, data collection, variable extraction. You can see there the management of the resources, the service infrastructure, the monitoring. This doesn't come with the AI code itself, right? And so AI Sprint is basically providing a framework with all those assets and which facilitates the development of use cases, like, for instance, the one that I'm involved. And this one is actually the first one, the personalized healthcare use case, but there are two more in the project which are equally interesting. One that is called maintenance and inspection. This is about drones that take pictures of those windmills. And the third one is about agriculture, and this is about tractors that has cameras installed, and they basically modulate the amount of phytosanitary product to spray in the vineyards based on the volume of foliage. So 3 really interesting use cases, very practical. And one on personalized healthcare specifically is about stroke. So stroke, unfortunately, is the second leading cause of death worldwide. Its expenditure in terms of healthcare system is expected to be growing exponentially in the next years. And if you are lucky to survive a stroke, unfortunately, stroke is also associated with recurrence. So you are also, prone to have recurrent strokes. The good news is that 80% of those strokes can be prevented. And the secret to this prevention is basically in a continuous monitoring of the population for the risk of having a stroke. And how can we monitor the population for this? There are several devices, and here is where the edge component comes into place. Now, of course, ideally, we would like to have a continuous monitoring of parameters, like, for instance, the heart activity through electrocardiograms. The problem of the continuous devices is that those are implantable. You need a surgery to put this thing inside your body, and of course, this is not ideal. The more desirable are the minimal invasive, like, for instance, smartwatches like Fitbit, but those can only give information of electrocardiograms, for instance, in an intermittent way. You put your fingers in the smartwatch and you record 30 seconds at a certain point in your day, and this is probably not enough. So what we did in AI Sprint is to collect data, first of all, from something in between, a device that is a wearable device that is that is minimally invasive, let's call it like that. This is a vest that is made of a fabric, very soft, and very comfortable, with electrodes. I know this because I wear it myself. So this is produced by a Spanish company that is called Nubo. And why it's interesting? Well, first of all, because it's not so invasive. It's something that you wear on you. And it's also interesting because it's able to record up to 30 days continuously your electrocardiogram. And so this is super interesting because, of course, we want to have like a full view of the real world, what is really happening in a person throughout many, many days. So this is the device that we use, and what we want to do with this data. We want to develop AI models in order to provide a risk score of having a stroke. And this is, of course, like interesting from a prevention point of view. So practically speaking, the workflow, the architecture, in a way, in a simplified way, can be seen in these schematics. So we are collecting data from this device, this vest. We are using HPC resources in order to build AI models, specifically for predicting atrial fibrillation. That is an arrhythmia that is very important in stroke and is telling us about the risk. And once this model is deployed, we can use it, for instance, in smartphones in order to make inference, but using a different technology, using a less invasive technology, like, for instance, these smartwatches. Okay, this is a bit the idea. So, the data collection, we are still collecting the data, so we are in the process of this pilot study that we organized in collaboration with a patient organization and the company that manufactured this device. We collect data from different groups of people. Those are people, those are healthy people in one hand and people that survived a stroke. So we have the information from case and controls. We started last year in fall, then we have another group of people in spring, and then in the next month we are going to collect data from a third group of people. So what we do with this data is to train those atrial fibrillation recognition models. And since this is long-term electrocardiograms with a lot of people, we need, to distribute this, the training of this model, and we used this lib library. It was introduced in the talk before. So, well, those graphs comes from the actual original paper, and this lib, the advantage is that basically you can distribute the training of the model, and it's also giving a wide array of different models that you can use. So, for instance, on the right, you can see the speed up in terms of increasing the course, and you can see that it's actually much faster and than other possible solution. And in this particular case, this has been tested on a lot of millions of samples with a high cardinality of features. So I said before that we are still in the process of collecting the data, so what we did right now is to use public databases, in particular a database called Physionet. This contains electrocardiograms that has similar characteristics to the ones that we are collecting. And what we did are basically two things you can see there. So we analyzed the time series as they are, so the electrocardiograms as a time series, using this lib. And there you can see the types of models of learning algorithms that we train, from subtle vector machine, k-nearest neighbors, random forest, and convolutional neural network. All this is available in this lib. The performances, I didn't put the performances on the slide, but are comparable with the state of the art. And then something else that we did is to produce images of the spectrograms of those electrocardiograms. This is basically another way of visualizing, let's say, the information of this. And in collaboration with Politecnico di Milano, they developed this tool that essentially allows you to explore what is the best architecture, convolutional network architecture for working with images. And right, so basically going back to the workflow that I showed you before, all the pieces that we have right now are highlighted in yellow here. What we want to do more is the deployment on the edge and enabling the inference with smartwatches, specifically Fitbit. We are working with Fitbit right now. And also try to experiment with a federated learning. So when we train the model, instead of training straight away, training in a way using federated, let's say, a federated way of training those models. So this is, we will try in the next months. Yeah, that's all. So thank you so much. If you have any question later, I'm happy to reply.
So this time we don't fail. So the last talk is from Stefano Lorito. Stefano is a senior researcher at Geophysics Institute at INGV, Italy. Stefano is member of the steering committee of CET, in Italia is Tsunami Warning Center at INGV since 2013, and is also responsible for national tsunami hazard mapping. So now he will explain us his work upon probabilistic tsunami forecasting. No?
Okay. Great. Perfect.
Okay. First of all, thank you for inviting me to this panel, and be learning something yesterday in another meeting and in this one, so I'm very happy to be here. And I would like to acknowledge, first of all, that this effort started at INGV, but there have been many collaborators along the road in the HPC domain and in the scientific domain, Cineca, University of Malaga, NGI in Oslo, GeoZ in Poznan, University of Naples, recently with BC in Barcelona, in eFlows for HPC, and this effort has been funded during time by several national projects, first then Horizon 2020, then Euro HPC, and is going now ahead in the DTGEO and the new program of the European Commission. And so CHISI, flows, and DTGEO are the main framework, European framework where this workflow was developed after being conceived. Tsunamis are real. Before you ask it, also for Spain, you have a National Tsunami Warning Center in which University of Malaga is involved, which is led by IGN, and also other institutions participate, like University of Cantabria and several institutions for the sea level monitoring, and I think that the present status is that alert messages are sent to civil protection, while there is a national level discussion regarding the standard operating procedures to deliver messages also to the population and to finalize really the system, like in Italy. And the messages we have been receiving today, which are probably through cell broadcasting, we are doing the same in Italy to really cover the last mile for several emergency, several type of risks, actually. So historically, the tsunami community is a quite deterministic one, but the operational warning centers globally are progressively moving towards a more explicit uncertainty consideration and quantification to be conveyed, propagated into the warning. Because to give a tsunami warning, we have typically from minus to tens of minutes, for example, for the nearby coasts, and we have limited information about the earthquake which generated the tsunami, as you can see on the top. There you have limited information about the earthquake. You have to use your base knowledge regarding the tectonic of the zone, the faults, the past seismicity, everything you can use and combine with the real-time information, and to define a probabilistic ensemble of scenarios with different weights, different likelihoods of occurrence. Each of them must be numerically simulated, so that tsunami generated and the propagation for each of them of the ensemble member are simulated, in some cases in advance, and we have these pre-computed data banks of tsunami scenarios, or in the future, hopefully, also this will be possible also, let's say, in urgent computing mode in real time. The results of the tsunami simulations are to be combined with the probabilities of the sources to get a probabilistic estimate of the tsunami impact. So this is the first part of this kind of new concept or paradigm shift, if you want, in tsunami warning operations, which has this scientific component, which deals with the uncertainty treatment, monitoring, uncertainty quantification, and numerical simulations, in which also the HPC part sits, which goes as an input. And let me say just another thing. This can be also updated when new information come in, and data can be assimilated to improve the solution and to reduce the uncertainty. In the end, the probability must be converted into an alert level. People must know if they have to evacuate or not. So it's a yes or no decision. And there is a political decision to be taken on the level of conservatism to be used of the, let's say, acceptable risk. So the more you want to be conservative, the more you go to the tails of the distribution to the high percentiles. And this is a political decision which then can be once taken, when it is assessed, which is the level of of safety, the level of probability that one wants to take, then this corresponds to an alert level for the specific event, and this can be, this algorithm can be implemented in real time to get to green, orange, or red alerts, which imply different countermeasures from nothing to evacuation of a certain coastal region. So in this way, let's say the scientific component and the political component, the decision-making component are well identified, separated, and so they can be undertaken in the proper way with the different competencies and with uncertainty communication and at the interface. So this is the novelty of this approach. And presently we have two versions initially developed in the CHIS project. One is based, as said, on pre-calculated scenarios, a lot of pre-calculated tsunami simulations that can be interrogated in real time based on the event. And so this is the one up-to-date suitable for early warning use in minutes, less than minutes. The other one is based on the fly, even additional or new scenarios, brand new scenarios simulation, which at the moment is the state of the art is that this is suitable for rapid post-event assessment. When a disaster happens, for example, the civil protection, European civil protection mechanism needs to know what's going on before the picture is complete to start planning for their intervention for fast recovery. And so this period of time in which there is little information about what happened is covered by, can be covered by urgent computing and expert advice to the decision makers. So these are the two domains that are almost operational at the moment. And of course, we have been wondering and asking ourselves and testing that doing many simulations, doing high-resolution simulations, and so on is really helpful and useful. Of course, the faster the computer, the higher the resources available, the faster we can give an alert. But also, we have seen that if we explore better the uncertainties and in casting mode, and if we go to higher resolution, we can obtain better results and better prediction of the phenomena. So it's worth trying to do HPC in this domain. And but it's important also to test earthquakes and even more tsunamis are rare events. So we need to test to calibrate and validate our even assumptions and simplifications in all the workflow, because we need to use it operationally. So we are testing it at the global level with tsunamis happening all over the world in the past decades. There have been many, and we are testing them for our region, where the events are rarer, for example, than in South America, where you have faster convergence rates, so and more often bigger quakes causing tsunamis. We recur to synthetic models, so we generate Monte Carlo catalogs of earthquakes for which we generate synthetic tsunamis and use these synthetic catalogs to test the PTF, the probabilistic tsunami forecasting performance. We also made in 2021 in the World Tsunami Awareness Day, in the framework of CHIS, an urgent computing experiment. It was quite large for the time. It was a reservation of 800 nodes, each with 4 V100 GPUs, so that was a successful test, which, as said, could show that with respect to the and applied to the same earthquakes that OSEP has used to test his earthquake workflow, we could, this earthquake caused a measurable tsunami all around the Aegean Sea, and we could test that the more accurate simulation we do, the more precise the forecast will be. So, and with this I come to my conclusions. So we are starting to have a certain confidence that the PTF is generally compatible with observations, but we need to keep testing. Actually, we are formally asked before putting it into operation to provide more evidence and more testing, because of course it's a delicate decision. Also, there must be an international agreement about that, because we serve also other countries, and we are in a system coordinated by UNESCO. We can increase our accuracy using urgent computing, and for the reasons that I tried to explain already. So our work in progress is to test more with INI flows, and at DTJ we will keep building an evolutionary version that can be updated with data fusion if new data come in and if time allows, but also the other way around, reducing the size of the ensembles to make it more usable for those who doesn't have important HPC resources. And that's it. So I think this is having an impact, and we're very happy for that, because having an impact and being recognized also is important in terms of liability when you operate in this domain. And so we will be distributing this as a service in the thematic core service Tsunami in EPOS. And yeah, there is still PD8, that's the name of the cheese prototype, but PTF is being further developed in the other projects towards the Destination Earth program. And of course, we have a strict relation with the end users, like the Aristotle service for the European for the national civil protection and for the European civil protection, and our Tsunami Warning Center, which works in the UNESCO framework, which is very important to connect the science to the risk reduction. And that's it. Thank you very much for your attention.
Thank you, Stefano. So, first of all, if there are any questions from the audience, we can address now. Any question about these presentations? Okay, we have one there.
Hi. Very concrete question. I mean, thanks a lot for the presentations. Very interesting indeed. I would be curious in some of the examples you've given, if you could quantify some of the resources. So some of you or several of you have mentioned that these workflows allow you to access a huge amount of data and things like that. So any reference, I mean, if briefly, to the which volume of data are you analyzing with these workflows, and which, I mean, in case of like GPU or CPU, like how many GPU hours are those? Just to put this a bit in context, and whether this is a prototype that then eventually will become 10x or something, just to put. Thanks.
Just, I guess everybody has a different answer. In our case, in terms of occupancy, let's say, of a machine, I mean, we've been using, in the first case I shown, it was close to 3,000 nodes. So this, each of them 48 cores. And in other cases, several GPUs, hundreds of them. The most we can. The weight of the workflow itself in the whole process is way less than 5% at the moment. And that is leveraged by trying to understand what is the heaviest part in terms of data transfer. Data transfer can be a bottleneck. We try to have this inside, let's say, as much as possible. So whatever is a static data, something which will not change, in the Earth, let's say the properties of the Earth don't change eventually. This is pre-stored at the site, is available, and everything which is dynamic is something which is essentially moved quickly as a small portion. Plus, we post-process everything at the HPC sites so that only the final outcome needs to be sent somewhere. This is a matter of few megabytes. So in our case, this is more or less solved.
So I couldn't hear you very well, but I tried to infer anyway. because the sound is quite low frequency from here, so it's difficult to understand what you say. Anyway, regarding data, we have a few input data. If this is a question that's not demanding, then regarding resources, it's potentially very demanding. I put there some numbers regarding the computational resources used, but we are trying to find the way and the good compromise, and so it's still premature to say how much we can reduce, but I expect two order of magnitude reduction of the ensemble, meaning that instead of 800 nodes, we could use much less computation also. It can become, so we could then explore how much we can go towards inundation, because something I forgot to say is that our results are offshore, and then it has, we will need much more computational effort to go in the details of the inundation. For the moment, we do only projections. So what we will be saving in terms of source uncertainty exploration probably will be, we have then to explore and also to combine with AI how much we have to again charge in terms of higher resolution for inundation. And that's it. Don't know if I answered.
Okay. Do you want to ask from your side?
Well, I'm not completely sure if I understood the question, to be honest, but. Yes.
Enabled processing. So I was just curious whether this was 1 gigabyte or 100 terabytes.
No, it is terabytes.
Hundreds of terabytes, or yeah. Sorry.
I don't know. No, I don't think it is hundreds of terabytes, but.
I mean, that was my question, basically, to put that reference in that
I would
log
say
scale,
between the 100 of gigabytes and the terabytes. That's the point is that when you use a distributed workflow management system, you incur in an overhead. What I'm trying to say is, imagine you use an SVD, for example. You first need to write down the SVD, and the SVD is, in essence, a big matrix, okay, double precision. But then you need to analyze that matrix, and you need to do it distributed. So aside from the memory you have on every single node, you incur in a penalty because some of the data need to be packaged and sent somewhere else. And there is, they are not actually written to disk, but they are serialized and packaged because you need to essentially your simulation is packaged and sent somewhere else, okay? And this means it's like you're making a copy of the entire memory of your. So if you normally would occupy one for a simulation, you occupy 3 times more in terms of memory, okay? So I'm not sure if it answers, but it is in that range, up to a terabyte or something like this, I would say.
And in the case of my use case, so for the moment, again, it's a similar situation. Like the amount of data is not so much. Actually, we are using this public database, but we expect this to be, requiring much more resources. So the distribution that we have done so far, it took like few nodes of Mare Nostrum, but this is going to scale up when we have more data. But the more challenging aspect, at least in my case, is going to be at the inference level. So imagine like a lot of people having their smartwatching and they want to check this prediction all the time, and so those requests are going to be like a lot, and so this is going to be a very challenging aspect as well.
And this inference, you foresee it as a let's say AI as a service, let's say it's a remote call to a.
We are actually using, we are developing something using a library called Oscar. This is a serverless tool for making inference of AI models on demand. And so it's, we expect this to be immediate and not requiring so many resources. But of course, this needs to be tested.
Any other question from the audience? Yeah, one, Alberto. Okay.
One specifically for Davide. I didn't understand one or a couple of things from your explanation. So your goal is to train the model on the data, on the electrocardiograms, so that you can predict the occurrence of a stroke. But then you need to have events, or sequences that lead for a person that after that had a stroke.
Yes, so the data that we are collecting is actually kind of similar to a clinical trial. So we have two groups, healthy people, they are super fine, and then people that survived the stroke. So we can have a view on how the heart behaves in a normal condition and in a condition after a stroke. Knowing that the stroke can be recurrent, and most of those people actually have those atrial fibrillation from time to time, we can infer this score. Something that I didn't say actually is important is that we don't only have the electrocardiograms, we also have a questionnaire of risk factors, like for instance if they are obese, what kind of diet they do, so we also have this information. In an application, for instance in a mobile phone, this is information that you can enter, no? You can input this information. This plus the electrocardiograms and this prediction of atrial fibrillation is telling us, okay, you are fine, better to see a doctor, go to the hospital. Okay, so this is the idea.
And the other thing, the doubt I had is, so you expect that the training on data from the vest could be directly applied to data from the watch?
Exactly. So this was our first concern. There are actually the two technologies are compatible. So also the frequencies, the amplitudes of those signals are quite compatible. And there are a lot of limitations, of course, of these wearable devices, whatever it is. Because of the sensitivity of the signal, you have a lot of noise sometimes, but the type of information that you can capture is still valuable. And so even if we are training with the data from the vest and we are using it with the smartwatches, it seems to work well.
And if I can add, because I'm involved also in this project, because today is a day of alerts from tsunamis and on our phones. So the idea of the application, of course, is not to give 100% precision, of course. As Davide said, the idea is that this application will be used by doctors, hospitals, etc. So the user won't see, as we are used to with these devices, the alert, you have an atrial fibrillation. Maybe go to the doctor, or depending on the deployment of the application on the final usage, the doctor could already receive an alert from his patient, if is the case, if he is patient. So we don't want to give false negative or true, I don't remember. Okay, so for the moment we are training the models, okay, and trying to understand if the inference part is enough accurate, of course.
Also sort of ethical issues related to this, no? Do you really want to alert, like, the person needs to consent, no? To be informed about this. And the problem of the false positive is it's a problem. You want to alert like the person, and then especially if this is like, applied to big populations, no? This could also like create a problem for the health system, like it happened with alarm systems, and I think the same for emergencies and this. So yeah, very cautious about the actual then practical application of those things. This is another conversation, totally.
Okay. Any other question? So otherwise, I have some question for the panel also, maybe still related to these topics. So because we are talking about real world applications, tsunami alert, healthcare alert, etc. So the name of this panel is Programming Tools in Science. So we are in science where we test whatever, a lot of training, etc. But how do you see, above all, you that have experience in the tsunami alert, civil protection in Italy, for example, how do you see this application, this scientific application, when you move to the production systems? So are these tools still valid, or are just like toys for scientists? What do you think? Do you think that in science we miss this production phase?
No, we are clearly so close to have it in production. We must have it in production. For example, there was the Turkey earthquake, for which we dramatically over-alerted the entire Mediterranean. We caused evacuation in Ischia, for example, in Italy, or we stopped trains. So it was clear. And we had to do like that because when you have such a big earthquake, you have limited information, because at the moment, the tsunami warning system only looks at the magnitude of the earthquake and its location. So you can have basically very different mechanisms which are more or less tsunamigenic. If the seafloor moves vertically, roughly speaking, it will be more tsunamigenic. If it moves horizontally, like in that earthquake, which is dominantly strike slip, is called, you don't have a tsunami. But if you only look at the magnitude, a magnitude almost 8, it's potentially very tsunamigenic, and it could have been a disaster. This is how it works at the moment, because we don't have enough information. We have a decision matrix, we have to apply it, and to over-alert, and there is, this is another story, there is also no protocol to then cancel the alert rapidly if you don't measure anything. This is a complicated story and controversial, so I will leave this aside. But that said, in that and other cases, it was quite clear that we still have to test the accuracy of these methods, but they are better than what we have. You could argue that if I have a probabilistic prevision, I cannot say anything with just one event. It can be good or wrong only by chance, so you don't have the other way around, say, okay, I don't did good once, so my method doesn't work. This is the case for earthquakes. No, there are people who advocate against probabilistic methods because there has been an earthquake which somewhere has exceeded the design shaking. But that's not an argument, because it's, you know that you have a residual risk. So we are getting there. We need to test it, but we need to also convince the politicians to make the decisions. So they have to convert our probabilities into estimates, and we have to make it accepted also in the international community of the tsunami warning centers and other states that, of course, there is some inertia in the system. But the advantages are clear.
Okay, good. Also, most of those use cases come from European projects, for instance, and the requirement of showing that you are scaling up in the TRL is actually going to this direction. Like, show me that this is actually can be tested and demonstrated in a relevant environment, and even like brought to production. Yeah. Sorry if I interject, just curiosity about, no, since you were talking about, the type of information that can help reducing the uncertainty of tsunami. What type of information do you think can help? I was thinking like, I don't know, satellite images or things that at the moment I don't think you are considering, but what kind of other type of information could reduce this uncertainty in your experience?
Measuring the tsunami directly in the sea, because consider that we now measure the earthquake and we make predictions, say, about that tsunami. We should, and we are trying to densify the observation network to have early information about that tsunami, so we can really dramatically reduce the uncertainty. But we have to go in both directions, quantify the uncertainty on the one hand and reduce the uncertainty on the other one with more measurements. But at the moment, only direct tsunami observations are important, possibly in deep sea. Sometimes you have observations in near field for which you cannot do anything, so you must prepare people to react to natural signs, so like long and strong shaking and so on. They have to leave the coast because probably there will never be time at the same location to give an alert, but measuring it then can reduce the uncertainty of the forecasting for other locations. Satellite is not quick enough or still ready to be operational. GNSS, yes. So the GPS can be used to improve the earthquake characterization, which is another line of not research, of implementation to improve.
If I can make a comment, which is not about tsunamis, because I don't have a clue about tsunamis, admittedly. But at least for application in industry, those things are definitely interesting. The predictive models or the capability of packaging. But there is a problem because any supercomputer is a world. So it is very hard to do something on one supercomputer and then to bring it to another supercomputer. I mean, there was a big presentation about this, but I think that something that we are missing is on one side some sort of compatibility layer between different infrastructures. I would say some binary compatibility between, for example, MPI implementation. I really cannot understand why they don't provide some minimal compatibility with one and the other. I mean, I know that, for example, there are efforts about containers for this, but containers are not everything. There is also a penalty. That's a solution, okay? That's one step. But it would be also nice to be possible to have a binary that works on Mare Nostrum and then works on El Capitan. That would be a dream, okay? And that, at least as far as I know, it is not possible. But that's something that I hope will eventually become a reality sometimes, at least between compatible architectures.
Yeah, actually, this was also my question, because we are used to do a lot of tests. I mean, this is the basic of research, of course. Test new architectures, no? We have Mare Nostrum with, it's not just a flat, let's say, architecture. We have several options. Then when you go to industry, they have other machines that buy from Adriano. And what happens? So is this still valid? Actually, this conversation about usage of containers as solution or MPI, we had just yesterday with Stefano and Giuseppe, because we had a workshop on workflows with the flows for HPC and DTGEO, and this was raised yesterday. So what if I have continuous integration and development? So I have continuous development of the application, and suddenly the HPC center changes the MPI version. So everything is broken. So this is exactly what we discussed less than 24 hours ago. Yeah.
One comment about this. I think in terms of artificial intelligence, probably the wide adoption of containers software solution is a good thing. The diversity of the ecosystem is huge, but this standardization in terms of containers, that the majority of the software is agnostic in terms that runs on Kubernetes or whatever. So it's independent of the hardware, you can run wherever you are. So in any platform in the world, because it's Kubernetes at the end. The point probably more for simulation and modeling is more complex, because at the end there are a lot of dependencies in all the software stack, all the hardware dependencies in terms of the library like MPI and the implementation of the network, all of this. And probably this way that the team from BSc is leading on terms of other researchers in terms of workflows, that would be a good thing. We also are working in this direction that workflows would be in the future that the way of connect some of these workloads as well. Thank you.
Thank you. So another question. We're on time, right? Alberto, we're on time? Yeah? Okay. So another question that I have for you is, in all your presentations, include now machine learning, artificial intelligence, etc. So my question is, also today, Sergi presented that we will have specialized AI resources. So how this explosion of artificial intelligence and machine learning changed your way of doing science? Because artificial intelligence exists since 1950. But now everyone is using artificial intelligence. So it's a real need? It's something that you need, or you're just exploring it? So how has changed your way of doing science, this new programming?
Yeah, for us it would be great to have it because as I said, inundation simulation, for example, to go in more detail in what happens is still not totally reachable. So if we could emulate the tsunami simulations, that would be great. I'm not sure how much we are already able to propagate the uncertainty through the AI piece of the chain, and how much you need to pay, let's say, for training with respect to what you gain, and how much the results can be generalized, for example, side by side, because the local propagation is very dependent on the local features. So these are, to me, open questions, but hopefully, so it will be dramatically important, but I don't think we are there.
So in the field of biomedicine, it definitely changed the way in which we do what we do, but also like a lot of new challenges and new new problems, new issues came with this. First of all, the transparency, right? So in health in general, you really want to know what is going on. So you really want to know why the algorithm took the decision. So those black boxes, of course, are not very welcome in this field. So the field of explainable artificial intelligence, and try to open the box and see what is going on. This is crucial for biomedical application in particular. Not only, but in particular biomedical applications. This is in one hand. The other hand is also that in most of scenario, you don't have enough data to train like big models. And again, in health, this happens a lot, especially in precision medicine. So imagine that you have like a big cohort with a lot of people. And then you start saying, okay, now I want to build a model only for women of this age, of this race, of this ethnicity, whatever. You end up with like few patients and you have few data. So what do? You cannot train like a super deep neural network with this. And so you resort to statistics, you resort to simpler models that are more explainable, so it's also good, but you cannot really use AI anymore. So it really depends on the context as well. Mm-hmm. So yeah, I mean, there is not a definitive answer to that, but this comes with a lot of reflections that need to be brought to the table.
Okay, thanks.
Well, it is a difficult question. The answer, it is important in our world, but also it is is not black and white. What I'm trying to tell is, one use is that you can think of artificial intelligence as deep ignorance. Let me try to explain it. You can generate data, and then you can try to have an interpolator out of your data, okay? And that's a surrogate, if you like. In that sense, it has a meaning. It is like doing a regression, okay? Then there is this has an interest, of course, but then there is another level in which you try to blend 30 years of computational mechanics and of simulation, and to use artificial intelligence in the points at which it is still lacking. And this is where a lot of research is going on now, but also where the bar to enter is very high, because, I mean, the new model has to compete with a model that has been working for 30 years and has been polished, and so in there it is slowly, it is more incremental. So we are in progress, let's say.
Before you go, you make me also think that we really need to start storing, preserving, curating simulation data. for what you said. And we feel as users, for example, of praise, or that this is kind of missing. So we are asked, if we get a praise project, we are asked to leave the room, and also quickly. So we have a huge problem in storing terabytes and more of data. And this data from previous simulations that could be used, as you said, are not then easily available to the community for reproducibility, but also, for example, to train new AI-based models. So I don't know, perhaps this is relevant here to urge you to think of that and to start really preserving the simulation data, not only the normal data.
Just to comment on that, I think Stefan is totally right on this. So one of the biggest uses that we have for machine learning in this case, and one of the biggest opportunities for people which are simulating processes, is specifically complementing the data, as David was saying. I mean, sometimes we just don't have enough data for a certain system, but we know its behavior. So we can try to complement observations and simulations. And that is something which is really working for us. We have been doing this for a long time. In our field, in seismology, this happens with earthquakes. Earthquakes, I mean, we have been recording them for about 100 years, and that recurrence is not quite enough to study or analyze what the outcomes are. So what we do is we simulate 500,000 earthquakes in a region, and we complement that with the observations, and that data set, which is a mixture of synthetic and real data, is what we use for training models. And those models are able to predict very well what actually happens. So this is a huge opportunity for all of us. Of course, again, the big gap is we are not storing that data. If you think about CERN, for example, that huge particle collider, they're storing data, I think, for 25 years, something like this. And it makes sense. It costs a lot to build that infrastructure. There's data there. Why would you dump it quickly? Just keep it. Somebody will use it. We are doing exactly the opposite. We are running simulations, and we are just dropping it out because there's no room for this data, and we are just dumping it all away. That's wrong. So somebody has to think about it and provide, let's say, some real long-term storage for all of this information, as much as accessibility, findability, and all of these principles, which can provoke other people to use this data in the future to produce something completely new. Also, I think that bothers me a bit regarding the machine learning field is that perhaps we're now colliding in terms of resources with people which we were, or not typically, let's say, or competing with us. And it happens because of GPUs. GPUs are the best thing for simulating things, we know that, but incidentally are the best thing to train models, data models. And that's a strange situation for everybody, okay? So these huge supercomputers, more and more, are NVIDIA-based GPUs, something like this. And incidentally are perfect machines also to train other things which have nothing to do with what we've been doing for a long time. So I'm also a bit worried, let's say, what will be the future. I mean, how we'll be competing, let's say, with this scarce resource, which are the best possible compute units available. Just a note.
Thank you. So I think we are perfect on time. So if there are no more questions, we can close this session. Thanks for the panelists for the contributions. And Alberto, thank you.